Hello, myself Dr. Sumanayal, Associate Professor, Department of Electronics and Telecommunication Engineering, SSIT. Today, we'll discuss on the topic of satellite link design. So, designing the satellite is actually a very complex process which involves the different factors such as the weight as well as the cost of the satellite. As the weight of the satellite increases, the cost also obviously increases. There are few other factors which influence the system design. So the first thing is the choice of the frequency band. So frequency band, whenever we want to design the satellite, the first thing is the choice of the frequency band. So whether it comes under L band, X band, K band, Ka band or Ku band. So these are the frequency band we need to mainly focus on which frequency band we are going to design the satellite. And the second one is the atmospheric propagation effect. So atmospheric propagation effects mainly due to the sky noise temperature or it may be the gaseous effects like that. The changes with respect to atmosphere is the choice of the another factor which influence the system design. So the next thing is the multiple access technique. So in multiple access technique we have different types such as frequency division multiple access, time division multiple access and code division multiple access. So based on the type of the multiple access, there are the factors which influence the design of the satellite. So next is coming to the basic transmission theory. So consider isotropic source here. So the isotropic source means at the transmitting end, so the power which radiates uniformly in all the direction we call as the isotropic source. So I am considering the isotropic source. So EIRP is the effective isotropic radiated power. Since we are at the transmitting end, so power we are taking as PT in watts. So this is the flux density produced by an isotropic source and area is A meter square. So which is in the free space. We are taking the transmission at the free space. So area A is equal to A meter square and flux density F with watts per meter square. So the flux density is given by PT divided by 4 pi r square watt per meter square. So where PT is the power at the transmitting end, So next is considering the gain of the antenna. So gain of the transmitting antenna is given by G theta for a unit solid angle is given by G theta will be equal to P theta divided by P naught divided by 4 pi. So considering a unit solid angle, so P naught is nothing but the total output power divided by the unit solid angle. So next is considering the flux density and also gain at the transmitting end. So we have power PT and gain GT divided by 4 pi r square watt per meter square. So here, so now we will consider how to design a satellite link and also arrive at an equation for link design formula. Okay, so consider a transmitting antenna in a free space. So which radiating energy, that is power PT, uniformly in all the directions, which is called as PT, that is power at the transmitting end. So isotropic source, so this is the area A meter square and flux density F watt per meter square. So this is the figure of flux density produced by an isotropic source. Now the flux density is given by PT divided by 4 pi r square watt per meter square. So now the gain of the antenna, any gain of the antenna, real antenna, is defined as the power radiated per unit solid angle to that of the total power. So whereas G theta is the gain of the antenna at an angle theta, that is in the direction of theta direction, and P theta is actually a power per unit solid angle and P naught is the total power. So the flux density is given by F is equal to PT GT divided by 4 pi r square, where this product PT GT we call as the EIRP. So EIRP is nothing but effective isotropic radiated power. So the product of PT and GT. So this product we call as EIRP, effective isotropic radiated power. So now till now we have discussed at the transmitting end. Now coming to the receiving end, we have the same isotropic source which radiates energy in all the direction, and we are considering the flux density F watt per meter square with respect to the receiving end. So the area again it is A meter square. Here the gain of the antenna we will take as GR, that is gain is at the receiving antenna, so GR. So previous one, the gain at the transmitting antenna we are taking, so that it will be GT. So the flux density is given by PT divided by 4 pi r square watt per meter square. So next, the received power, now it will become the flux density into that of the area. So the flux density into area divided by 4 pi r square watt. So at the receiving end, that is power received will be equal to flux density into the area that we have considered, which is represented in terms of watts. So the effective area will be actually equal to the aperture efficiency into the area at the receiving end. So the power received will become PTGT. So it is multiplied by PTGT into AE divided by 4 pi r square, which is represented in terms of watts. So this this PTGT is nothing but effective isotropic radiated power. Now we will consider with respect to the gain. So the gain of the antenna is given by 4 pi AE divided by lambda square. So similarly, PR will become PTGT into GR divided by 4 pi r divided by 4 pi r by lambda whole square, which is represented in watts. So now we are going to substitute AE, effective aperture, that is AE, in equation 6. So here, so then power received will be equal to PTGT divided by 4 pi r square by lambda whole square. So this we call as the satellite link equation. So here this can also be represented as 4 pi r by lambda whole square. So this we call as the path loss, and PT into GR, which we can also represent as the EIRP into GR divided by 4 pi r by lambda whole square, because the product PTGT is nothing but EIRP, so that you can represent that in PTGT also. So the same equation can be represented in terms of decibels. So PR will be equal to EIRP, as I told. So PR will be equal to, so this one is nothing but EIRP. So PR will be equal to EIRP into GR divided by path loss. So path loss you can write like this, path loss. So in watts. So the same thing I am writing in expressing in terms of decibels. So PR will be equal to EIRP plus GR minus path loss in dB watts. So EIRP will be equal to 10 log to base 10 of PTGT dB watts, since the product is nothing but PTGT and GR is nothing but 10 log to base 10 of 4 pi AE divided by lambda square. Again, the path loss can also be written as 10 log to base 10 of 4 pi r by lambda whole square. So this having the square, you can also write as 20 log to base 10 of 4 pi r by lambda which is represented as dB. So this is the representation in terms of decibels. So the same equation considering various losses. As I told, designing the satellite involves many atmospheric changes also. So atmospheric changes means there will be so much of losses also at the transmitting end as well as at the receiving end. So we considering the losses, power received will be equal to EIRP plus GR minus LP minus LA, that is attenuation losses and losses with respect to receiving end, so which is called as minus LRA, which is represented as dB watts. So this is the diagram of the satellite in which the effective isotropic radiated power, which is PTGT, so the loss at the transmitting end and at the receiving end, so loss will be equal to LTA at the transmitting end and atmospheric losses LA, and earth station antenna gain at the receiving end loss, which is called as LRA. LTA is the loss with respect to transmitting end and LRA is the loss with respect to the receiving end, and this is considered with respect to the low noise amplifier. So the satellite link equation, so it can be represented as power received will be equal to PTGT-GR divided by 4 pi R by lambda whole square. So the same equation can be represented in terms of decibels. Further, it can also be expressed in terms of considering the various losses involved in it. So this, thank you.